Hi, everybody. Yeah, I'm Kimberly McGuire. I'm from Bitcraze. And like it was already said, I'm going to talk about ROS2 and the Crazyflie. It's actually together with Wolfgang Hönig, but unfortunately he couldn't be here right now. He's from the IMRC lab of TU Berlin. So just kind of a bit of a background of the parties involved in trying to get the Crazyflie to talk with ROS2. On the left side, you see Wolfgang Hönig. He is from the Intelligent Multi-Robot Collaboration Lab. I hope I have it correctly. And on the right side, you can see everybody, all my colleagues at Bitcraze, all 6 of them. So actually, Bitcraze started by Tobias, Marcus, and Arno, from 3 from the top. They started the Crazyflie 1, and it became so popular actually that they started Bitcraze as a company to start selling the Crazyflie. By now, we're actually already at version 2.1. And as you can see, obviously, it's a quad rotor with brushed motors. It's about 27 grams. It has 7 minutes of flight time with the stock battery. And it kind of distinguishes itself as having a modular design with expansion decks that you can give the different type of positioning system, or you give it an LED deck, name it. We have a bunch, I think 15 in total. And it has open source firmware and software, and it has open hardware. So we provide the schematics of it at least. And pretty much the biggest clientele right now are academic researchers and also industrial researchers. But I must say, I think probably most people that use it are researchers in universities. So here's kind of like a compilation of some of the work that has been done with the Crazyflie. So you can see on the right all the universities that have been represented in this compilation video we made about 2 years ago. Should probably make a new one. But perhaps that kind of gives you an idea of what the Crazyflie is used for. Fernando, of course, from this morning's talk at 9 o'clock, talked about the Kummer Robotics flight stack. I hope I pronounced it correctly, but they've been using it well in their lab. But at least the work that I'm going to present today is not related to that. It's actually more low level. I don't know if anybody attended that talk. It was a very interesting one. Oh, there you go. Grasp Lab, that was it. Of course, I'm here at ROSCON. So why is the Crazyflie interesting to you? Actually, if you just look at the last 2 robotics conferences, ICRA and ROS, there were 28 papers that had Crazyflies in them. 14 were using our own maintained software. We have a Python library. But the other 14 were actually using a ROS as a communication framework. And of course, I would like to give a shout out to eProsima, because they actually provided a very nice demo of the Crazyflie with micro-ROS actually. So I'm not going to talk about micro-ROS implementation of Crazyflie today, but I just wanted to mention this because that's pretty cool. So the reason why half of the users have been using ROS is because of the Crazy Swarm 1 project that was developed by the University of Southern California and still currently maintained by James Price and Wolfgang Hönig. And as the name suggests, they made it so they could be able to kind of handle flying with 49 Crazyflies at the same time. So, yeah, ROS2. Why? Obvious reason, ROS1 will end. Also, we would like definitely to make use of the much improved communications. It also kind of gives a chance to redesign the ROS package from the ground up to clean up some interfaces and features. And for that, we set up a couple of design requirements. It's still pretty rough, but we want it to be a bit more of a modular design. The Crazy Swarm 1, or the ROS1 Crazyflie package, was pretty much only one single node communicating with the Crazyflies. We also want to focus on better ROS2 integration. Also, it should be way more easier to use and better tested. For the autonomy support, we would like to have support for multiple positioning systems. The ROS1 version already had that quite a bit, but we definitely want to keep that. And we want to have not only support for swarm of Crazyflies, we also want to have support for, better support for a single Crazyflie as well. And also, we would like to make it easier for researchers to connect to external ROS2 packages. Simulation, we find very important as well. I'm not going to talk about that much during this presentation, but what we definitely want is a more easily switchable between real and the simulation platform. We also want to provide different backends. Using simulated are more useful for swarms versus ones that has a better rendering engine for some kind of vision-based research. And also we want to kind of provide some kind of hybrid software in the loop. So this is kind of an overview of the Crazyflie ROS2 architecture. The project itself still officially is called, unofficially called Crazy Swarm 2. But I'm just going to call it Crazyflie ROS2 package for now. And the status is definitely still on development. Nothing is set in stone. But this is kind of the rough ballpark of what the first steps that we want to go for. The most important node is the Crazyflie server. That's the one that connects to all the Crazyflies, makes all the transfer all the logging to topics and whatsoever. I'm going to explain it in a bit. We also have a Crazyflie ROS2 Python API, which is kind of like a wrapper around all the ROS2 services that makes it possible to control the Crazyflies or the swarm with just a few lines of code. And of course, the simulation should be able to do the same as the Crazyflie server. But let's first focus on the Crazyflie server. This is the ROS2 node that actually connects with the Crazy Radio PA, which is the main communication device or dongle used to communicate with the Crazyflie. And one Crazy Radio can connect with multiple Crazyflies at the same time. They share about 450 packets per second, 26 bytes per packet to be exact. And unfortunately, due to the hardware of the Crazy Radio, it's not possible yet to make one node per Crazyflie. But yeah, perhaps in the future, but I'll come back to that. It has different backends. It has a C++ backend that is more meant for broadcasting. We also have a Python-based backend as well. And pretty much what the Crazyflie server does is setting up all the topics and params and setting up all the kind of the flight services. So what does it kind of mean to connect with a Crazyflie without ROS? Each Crazyflie has a unique URI. They have to be, especially if you're flying with multiple, they have to be unique. And once you have that, you can put out a request to get a table of content of the logging and param variables that are defined in the firmware. So once you have received that, you can start sending commands, maybe start up some kind of data streaming. And of course, then you will get telemetry back from the Crazyflie, and then it's when you're considered fully connected. Although technically it's a stateless communication, but let's, for the sake of simplicity, say then fully connected. Just to make things clear, because there are some definition misfits, logging in the Crazyflie definition actually means a data streaming of variables in real time. And parameters is more like ROS2 parameters. It's the kind of the reading and setting of variables. In this case, the in-firmware variables. So the Crazyflie parameter handling with ROS2 parameters goes like this. Once you've received the table of content of the parameters, the Crazyflie parameters are turned into ROS2 parameters. It's pretty much one-on-one. Then we have an initialization file, and that actually sets the Crazyflie parameters according to whatever is in that file, a YAM file. In the meantime, it also sets up a ROS2 parameter change callback, which is a really nice feature now that it's actually easier in ROS2 that enables us that we can actually change parameters in runtime so that it will be changed also on the Crazyflie itself. Logging handling is a little bit more complicated because you cannot simply not stream all the data back that's possibly that exists on the Crazyflie. That is just not possible. So once you're fully connected, you've received the table of content of the logs. You will set up log blocks from the YAML file. And then you set up log block callbacks, which whenever it gets the data in, it will transform the Crazyflie logs into a ROS2 topic that is the closest in terms of type, like integer, integer, float, float. And also it will also set up the services to add and remove logging in runtime. So you can, while it's flying in the air, you can pretty much choose whatever variables you want to see at that moment. And you can also, of course, remove logging as well. This is a log block. That is the 26 bytes that I was talking about, the packet at least. So you can give it a frequency. You can give it a couple of variables that you want to see. And this is kind of how the YAML file looks like. Probably people in the back are not able to read it, so I won't go too much into it. But pretty much you can also set firmware and parameters either for the entire swarm or for each Crazyflie type or robot types or per robot. It's probably easy. Actually, I wanted to show a live demo, but it was a bit difficult because I couldn't use my own computer. But I made a video. So here you can see that I've changed the URI to the one that's the Crazyflie. I have an LED deck. I want to change the effect. So let's make it a solid LEDs. So the means is that once I enable the Crazyflie server, which is now currently on, you see that the LED deck has turned into a solid color. And then this is actually also in RQT. I was able to look at all the parameters that are currently set. And then I want to, for instance, in runtime, change the color of the LED deck, which is very simple. So then blue, maybe a bit of red. So this is then all happening there. And in the meantime, I realized that I want to maybe check out the IMU values, for instance, or the current attitude state estimates. So now I actually have set up a log block that is able to do that. And then these topics are then created in runtime. Of course, just looking at them at 10 Hertz doesn't say that much, so let's use the nice spotting functionality of RQT so I can actually start looking at some IMU data, or state estimates to be exact. Well, we haven't really seen anything flying yet, maybe a little bit boring. So let's try to bring in the introduction in order to actually come to a flying Crazyflie autonomy swarms, right? So first of all, basics about positioning systems. At least the Crazyflie is able to handle quite a bit. At least in motion capture, we have an ultra-wideband positioning system. Lighthouse positioning system is actually a positioning technology used by virtual reality. So we're using that for the Crazyflie as well. And of course, you have the flow deck that has an optical flow sensor. So now I'll put, for instance, the flow deck on the Crazyflie. And then I actually define a couple of special logging, let's say, that actually doesn't only translate the logging to the actual topic, but it actually has a specialized topic type and also a transform. In this case, for instance, the pose. The transform is also admitted if I enable this default topic. Yeah, and then you can see it in RViz. That's actually quite nice. Still not flying that, I'm almost there. Flying, yeah. It's a quadcopter, right? It needs to fly. So there's a couple of ROS2 topics that are enabled. So some that are for attitude control and velocity position control. So that is handled with topics. But we also have a couple of ROS2 services that the Crazyflie server sets up. So take off to a certain height, land, go to upload a trajectory or start a trajectory, and of course an emergency service that just turns off the motors if there's something wrong. And you can either do that for the individual or a swarm. So either you look up the Crazyflie name that you have defined in your YAML file, and you say take off, then only one Crazyflie takes off, or you can say all take off. So here you kind of see 5 Crazyflies, and they're flying with the lighthouse positioning system. And also kind of like a small demonstration of the Python wrapper that I was talking about earlier. And they were using the services all takeoff and all land. Little bit of background information, just kind of to step back. A while ago, I was a beta tester for a nice course called Build Mobile Robots with ROS2 from Matt Sadowski. And it was in a gazebo. You would build up a mobile robot and everything. And yeah, really nice course. But of course, as a true roboticist, you would like to see it working on an actual platform. So I thought, why not the Crazyflie? So yeah, so then during the summer, I actually made a little bit of a hack project out of it, that I added a flow deck to a Crazyflie for visual odometry, and then the multi-ranger, which is a deck with 4 horizontal 1D TOF sensors. And then I made some kind of simple mapping node. I connected also with the nav2 package as well. But it was super hackish, and it was a lot of fun to do. I hard-coded everything, but of course Wolfgang came to me, he's like, okay, we need to probably make this a little bit more official and put it in the ROS2 package. So yeah, I made some default topics, just like the pose default topic that I was explaining before. For the multi-ranger, change that to scan, and the flow deck to change that to a transform for odometry, and also as a topic. And then I was able to connect it to the SLAM toolbox. Do be warned, I definitely had to turn the scan matching off. So technically, it's only the mapping part of it. And I would then also assume that it's solely based on the flow deck odometry. But as you can see, I was able to make a nice map of the room. And once you have a map of something, maybe you'll be able to navigate through it. So with that map, I was able to connect it with the nav2 bring up package, which I learned during that ROS2 course. And then I, of course, had the other trouble, a Crazyflie is not a driving robot. So I made another node that was able to handle the incoming twist messages of the nav2 node, and actually made sure that the Crazyflie was in the air first before it actually reacted on the twist messages. You see me now actually putting now an obstacle in the Crazyflies. It's able to detect that, but I also, in this case, I had to make the robot much bigger than it actually was. It's not a full 360 LiDAR that's actually carrying, so it has definitely limited sensing. But at least, you know, it didn't crash, it still navigated around it. It was maybe a little bit more conservative than it could have been. But that wasn't really my purpose, to make the perfect navigation application here. This is purely only to kind of show you that you're able to connect it with staple packages for navigation and the SLAM toolbox. It's a demonstration in that sense. So how about the simulation nodes? Yeah, during the summer hack project, I actually played around with webbots. So I made a simulation node in that. And in preparation with that, I actually made sure that the Crazyflie model was in the latest webbots 2022B release. Unfortunately, I didn't have the time to fully implement it to the ROS2 package as is. But that's definitely one of the next plans for sure, once the webbots ROS2 driver has been fully released. And of course, like I said before, one of our design requirements is to provide different backends. So the gazebo is definitely one of them, but we also want to have like a good choice between good simulations that are possible for swarming, and yeah, so yeah, because it's still the unofficial name is Crazy Swarm. you would like to have a better swarm simulation for that. But so if anybody knows any good simulators, let me know. So what's next? Like I said, implement the simulation node with more backends officially. Also interesting to note is that we actually are developing the Crazy Radio 2 development. Currently we also are tweaking out smaller issues. Also, like, yeah, with the Crazy Radio 2, it might be also more possible to have different nodes per Crazyflie as well. And hopefully, maybe we'll be presenting the first release of this package at one point.
All right. Thank you very much for the presentation.